Welcome everybody to another day of Math 210. So to review from last time, we had talked about the fundamental theorem of calculus, part one, which said something like, if you want to take a definite integral from a to b of f of x, so if you want to find the, make sure my audio is okay, looking good. If you want to find the signed area under the curve y equals f of x from a to b, then what you can do is you can take, if you can find an antiderivative of function f of x, that is to say, if you know that f of x is continuous, there were some assumptions there. F of x should be a continuous function, and there should be an antiderivative, which I've been calling capital F of x. Antiderivative means that when I differentiate capital F of x, what I get back is the function that I started with. And what we learned was that fundamental theorem of calculus part one gave you a way of calculating this integral by simply taking an antiderivative and then evaluating it at the endpoints, capital F of b minus capital F of a, which we notated by taking capital F of x and then writing this vertical line and then putting a and b there. And this was motivated for us by physics, where f of x was the velocity, and we saw that displacement was the signed area under the velocity curve on the one hand. But we saw that, on the other hand, displacement is simply where you ended up minus where you started. So on the other hand, displacement was nothing but the difference between your position, located at the two different times. And position is, of course, an antiderivative of velocity. So that's where that all kind of came from. But of course, this is completely general for any function that's continuous that admits an antiderivative like that, then this will be true. It's fundamental theorem of calculus part two. So I sum this up by part one, excuse me. So I sum this up by saying that antiderivatives are useful in that we can use them to calculate an integral. And of course, we saw lots of examples of how to actually calculate integrals. Now, what about fundamental theorem of calculus part two? So what does that say, and how do we put it into context? So if part one says that antiderivatives are useful, part two says that antiderivatives definitely exist. And they also, and part two also explains the reasoning for the notation that we use when we talk about indefinite integrals. Okay, so let's state it though. So once again, you start with a continuous function, f of x. CTS for continuous on maybe some interval from a to b. And now this time, I'm going to define for you a new function called capital F of x. And this is going to be like the signed area under the curve from a fixed point to x. So what I'm going to do is I'm going to write this as integral from c to x, integral f of t dt. And where the number c could be anything, so like you can just pick this number c to be whatever you want, as long as it's inside the interval. Doesn't really matter other than that. So I'll draw for you a picture of what I'm talking about. So you take maybe some function that's continuous on the interval from a to b, you pick any point you want, call it C, and then you define a new function, and the input of the new function is x. So here's an input, x. This is a function whose domain is x between a and b. So you could pick any x you want between a and b, that's the input, and the output is going to be the signed area from c to x of f of t. So in this particular situation, the output is going to be the area under the curve and above the x-axis of that little slice. And if you pick an x less than c, that's fine. Your output in this case would be a negative number, because you'd be going from, and you'd be integrating from c to x, which is the negative of integrating from x to c. So it doesn't matter whether x is over here or over there. You can still write down this definition. It's no problem. It's the signed area under the curve from c to x. So is that clear? I want to make sure that definition is really clear. So are there any questions or comments from anyone about that? You start with lowercase f that's continuous. You define a new function where after choosing any point c that you want, you define a new function that gives you the area from the signed area from c to x. And then fundamental theorem of calculus part 2. This is the theorem, THM for theorem. Fundamental theorem of calculus part 2 is telling you that under these assumptions, that f is continuous, that you've picked a point c, you defined this capital F of x, then f prime of x is equal to your integrand. So in other words, this is telling you that capital F of x is an antiderivative of lowercase f of x. So if part 1 said that antiderivatives are useful, part 2 is telling you that antiderivatives exist, which is nice. And we've also had this previous theorem that says, given a function, any two antiderivatives must differ by a constant. Because given a continuous function, if you've got two antiderivatives, their difference, you take the derivative of their difference, that would have to be equal to 0, and so that difference would therefore have to be a constant. That's where that came from. So in fact, given a function f of x, any antiderivative must be equal to this expression, like plus a constant. So for instance, let's do an application. Let's take, I'll show you how to prove this theorem in a minute, but assuming it's true, let's do an application. Let's take lowercase f equal to cosine of x. And let's take interval from a to be 0, and b could be 2 pi. Let's take c to be equal to pi over 2. I'll even modify the picture here so that it goes along with cosine. So it starts out at 1, it goes to 0 at pi over 2, goes to -1 at pi, goes back to 0 at 3 pi over 2, and then climbs on back up to 1. So there's like one period of cosine function. You've picked c equals pi over 2, and then now you've got a new function, f of x, that, pick any x value, it'll give you the, in this case, the output would be capital F of x would be the negative of this area that's like above the curve and below the axis. So fundamental theorem of calculus tells us that if I take integral from pi over 2 to x of cosine of x dx, then the derivative of that will be equal to cosine x. So in other words, this function capital F of x is an antiderivative of cosine. We also know another antiderivative of cosine. So I know that if I take capital G of x, call that sine of x, then we know, or at least we should remember that the derivative of sine of x is equal to cosine of x. So now I've got two separate antiderivatives of little f of x. I've got two separate antiderivatives of cosine of x. One of them is sine of x, and one of them is this, integral, this area, this signed area under the curve business. And we have this theorem that says that if you have two antiderivatives, they must differ by a constant. So in other words, it must be true that sine of x is equal to g of x, sine of x, is equal to f of x plus a constant, is equal to this integral plus some unknown constant. Or if you'll let me write the unknown, I mean, it's an unknown constant, so I may as well call it negative c. There's nothing wrong with that. And if you let me write this on the other side, like add c to both sides, sine x plus some constant c is equal to this definite integral from pi over 2 to x of cosine of x. You can figure out what that constant c is by calculating this with fundamental theorem of calculus part 1. But for now, I just want to link this back to the idea of indefinite integral. Remember that bizarre notation we used for antiderivative? We defined the antiderivative of cosine of x to be this symbol. And that's what we did, right? We said the antiderivative was this, we called it an indefinite integral. When we think of like all antiderivatives together, the function plus or minus a constant, we called that the indefinite integral of cosine of x and wrote down sine x plus c. And here I'm noticing that every single antiderivative of cosine has this form. So hopefully that motivates for you like why we choose the integral with no bounds to just generically refer to an antiderivative or an indefinite integral. Because every antiderivative will have this form where you have like a variable up there, and changing around this lower limit will change around the value of the constant c that happens. So that's just something I'd like to remark on, why it kind of makes sense that we use this notation for antiderivative that comes from the fundamental theorem of calculus part 2. Okay. Any questions or comments? Looks like there's one question that I may have explained while I was speaking just now. Let me give you a quick class exercise. So I will show you the proof of Fundamental Theorem of Calculus Part 2. But before I do, let me give you a quick class exercise to help you understand what's going on or check your understanding. So I've given you an argument that shows that the integral from pi over 2 to x, and I kind of wrote that a little badly. I should have written cosine of t dt. Remember the setup here is we're going from like 0 to 2 pi, and I'm choosing this lower limit as pi over 2. And then if you pick any x value, then I looked at this function that took the integral of pi over 2 to x, which in this case looks like the negative of that area. And this integral from pi over 2 to fixed value x would be, I'd write this as integrand cosine t dt, where t is like the variable that goes from pi over 2 to x. So you really need to use a different variable to notate your integral, because the x in this case is kind of fixed. It's the input to this function. Okay, and so what I remarked on was that you could use Fundamental Theorem of Calculus Part 1 in order to calculate this integral and therefore find the value of the constant c. So my question is, please use Fundamental Theorem of Calculus Part 1 to find the number c. To take a few minutes. And if you need to look up what's Fundamental Theorem of Calculus Part 1, then definitely do that. It's your time and space to work on this problem. Please find that number c. After giving you some time to work, I'll show my answer. So I know that sine of x is an antiderivative of cosine of x. That was the point. That's where this came from. And Fundamental Theorem of Calculus Part 1 says you can use an antiderivative to calculate the value of this integral. So you just evaluate from pi over 2 to x. And there I went again. Sine of t would be the antiderivative of cosine of t, and then you evaluate this at the 2 points, pi over 2 and x. So this is sine x minus sine pi over 2, and sine x is what it is, and sine pi over 2 is equal to 1. So I'm faced with this equation that sine x minus 1 equals sine x plus c. Just rewrote that left-hand side there. I'm subtracting sine of x from both sides. I am noticing that c has to be equal to the number 1. And so changing this lower limit would give you different values for C, of course. So let's put all of this together. Let's try to prove it. And like the proof is technical enough. It involves the precise definition of the limit. The proof is technical enough that I'm not really equipped to show you all of the details. I'll leave that for Math 312 Analysis 1. But I want to give you the idea of what's happening. And what I'm going to give you is so maybe not like every single detail, but what I'm going to give you is very truthful in the sense that it is what is happening. It's the way mathematicians think about the proof. It's the way that I think about it. And so I hope it's really helpful for you. So we want to say we're given some continuous function on some interval from A to B, and we define this function capital F of X. As such, and we want to calculate f prime of x, and we want to show that the answer is equal to lowercase f of x. And when you're calculating a derivative, there's really only, there's no formula I can rely on or derivative rule that I can rely on to just do this. Like if I want to show two things are equal, then what else can I do but write down the definition of what it means to differentiate something, which is take limit as h goes to 0 of this capital F of x plus h minus f of x divided by h. And I want to show that this is actually equal to lowercase of f of x. And if I can do that, I want to sort of investigate this numerator here, this difference. So if you take a picture here, I'm just going to kind of like zoom in really closely. Let's say that you've got x. Imagine that h is an extremely small number, but I've zoomed in very far in the graph, and f of x being continuous, lowercase f of x being continuous, would therefore almost start to look kind of flattened out. I guess there's a number of things that it could look like, but we'll just sort of go with that. And if I want to look at f of x and capital F of x plus h, then yeah, what am I looking at? So point C could be anywhere, but for argument's sake, let's just say that it's right there. And then what I've got here is f of x is the integral from C to x. So it's the signed area of this region of the curve, right? Going from C to x, and in this case, C is bigger than x. So this would actually be the negative of that area. And f of x plus h would be, so what I should do is, I should label this x plus h, and you should think of this distance between them as a small number h. It's going to be rather a little bit more natural way to think about this. F of x plus h, capital F of x plus h, would therefore be the area under the curve from C to x plus h. And you've got this additivity of domain theorem that says something like integral from C, or integral from x to C, f of x plus integral from c to x plus h f of x dx. Isn't that the same thing as integral of from x to x plus h f of x dx, right? Don't we have something like that? Maybe this isn't exactly in the form that I want, because I want to look at, this would be integrating from c to x plus h. This one would be integrating from c to x. So maybe what I can do is switch these two bounds and put a minus sign. Remember, I can switch the bounds and put a minus sign. Remember that by definition, we extend integrals to allow, like, to the situation where a might not be less than b by making this definition. So if I start by like this additivity of domain theorem and then like switch the bounds and put a negative sign, I start to see that this was capital f of x plus h, and this was the negative of capital F of x. So it's telling me that this numerator is actually equal to the integral from x to x plus h. So it's telling me that this numerator is actually equal to the integral from x to x plus h of f of t dt over h. So f prime of x is the limit as h goes to 0 of f of x plus h minus f of x. And then, you know, getting an idea from the picture, but not depending on the picture for the proof, try to see what's going on. So this capital F of x plus h was like this area under the curve from h to x plus h. We use this theorem about signed areas that say additivity of domain. You split up the domain by inserting a point C. It doesn't matter whether C was between x and x plus h or not. And this, in the way that we drew it, it was between them. But you write down that theorem. You realize you can switch the bounds in exchange for a negative sign. It's something we set up before. It's part of our definition of integral. And therefore, that tells you that this numerator is nothing but the integral from x to this very small number, numerator from x to x plus this very small number h. And the key thing that makes the proof work now is the fact that this function, lowercase f, is assumed to be continuous. So if you're assumed to be continuous, then on a very, very, very small interval, you are well approximated by a constant. So for instance, this area, we erase this point C now because it's less relevant. So this area under the curve from x to x plus h is reasonably approximated this signed area under the curve from x to x plus h is reasonably approximated by just taking a left endpoint as the height and then using the length of the subinterval, which is h, as the base. So to draw a picture there, so that you can see what I'm doing is I'm taking this left endpoint, f of x, just using that as my height. And then I'm approximating the area as base times height, so h times f of x. And the question is, like, the technical details that make the proof a little bit more difficult is, like, what is this squiggly sign really mean? Like, can you really estimate the error to a high degree of accuracy between this and that? The answer is yes, you can, because f is continuous. But the intuition is that for a continuous function, it's well approximated by this left-hand rectangle, so long as h is a very small number. And therefore, if you take, if you just divide both sides by h, then f of x is well approximated by this integral divided by h. And that's what you've got right here. So when h is very small, this quotient is going to tend towards f of x. And therefore, when you take the limit as h goes to 0, that limit will actually be f of x, not like just close to it, but will literally be f of x. So that's how the proof goes. You take this function, you write down its derivative, look at that definition, you show that the numerator is equal to the integral from x to x plus h of f of t dt. You argue that that is well approximated by left-hand endpoint f of x times h. And you argue that therefore this quotient integral over h will tend towards f of x as h goes to 0. And the technical details that you learn in analysis are how do you do this exactly using the precise definition of the limit, not just saying that intuitively this should get closer and closer to f of x just because of the picture. But it's very much the same idea, and there's just a few technical things that you do under the hood to make it work. And I'd be happy to share those with you in office hours. Nothing's hidden, but it's not a fundamental part of this class that you understand that, so I'm not including it in the lectures. Are there any questions? So much more fundamental to the class is how can we use all of this information. And in order to do that, maybe I'll just pick some exercises from the back of the book and try to do them. So show you a sampling of the kind of things that we can get asked. So let's just start with this very first one. This is, the 5.5 exercises. So 5.5 number 1. It says that you're given some little f of x equals 4 minus 2x, and let's take a equals 0. So what it says to do is to create an area function a of x. That's what I've been calling capital F of x throughout this class. And the lower limit that I've been using, I've been calling c. They're going to call it a, so they're going to go from 0 to x of f of t dt. But they don't want you to do this with fundamental theorem of calculus. I think they actually want you to use geometry. To find a formula for a of x, and then it says verify the inverse relationship of fundamental theorem of calculus, meaning that integration is like inverse to differentiation. So meaning that you should be able to compute the derivative of a of x and find out that it's equal to 4 minus 2x. So let's Let's try to do that. So let's try to get a picture. So 4 minus 2x, so this is a line with slope -2 and y-intercept equal to 4. So if I take, here's x equals 0, if x equals 1, this is going to be equal to 2. If x equals 2, y is going to be equal to 0, so it's this. It's this thing. And let's take, for argument's sake, let's just let's take x in between 0 and 2. For x bigger than 2, you'll have like this area minus that one, but let's just take x kind of like in there. And then so a of x. A of x would be like the area of this shaded region, which I'll call like A, and it's going to be minus the area of the other shaded region, which I'll call B. So I need to find out those, well, yeah, it's not actually A minus B, is it? It's actually like, it's the area of the whole triangle minus B, isn't it? So the area of the whole triangle would be, it doesn't change. It, like the base is equal to 0, 1, or 0, 1, 2. Got this. I mean, this was my point x. Sorry, this is 0, 1, that's 2. And that was my little mark for point x. That wasn't part of the scale. So this has base equal to 2 and height equal to 4. So half of base times height is 1 times 4. So the area of the big triangle is equal to 4. And then you're subtracting the area of this small triangle and the base there. It's definitely 2 minus x, and the height there is definitely equal to whatever the y value is. Because if this is x, the height is y equals f of x, so that's 4 minus 2x, so half of base times height. 2 minus x times 4 minus 2x. Yeah, I guess I'll just keep working here. So multiply that out. That's 8 minus 4x minus 4x, and then plus 2x squared, right? So check if I did that right. And that's going to be dividing by 2. That's going to give us, it's going to give us a of x is equal to 4. So negative 4x minus 4x, that's minus 8x. So 4 minus 4x when you divide by 2, and then plus x squared. Do I have my signs messed up? Like my signs are like a little bit opposite what they should be. This base is 2 minus x, and the height is 4 minus 2x. So half of base times height. It looks good. When x is equal to 2, the area is equal to 4, which works out. But when I take the derivative of this, I get negative 4 plus 2x instead of 4 minus 2x. So that looks a little bit incorrect. So what's going on? Oh, I see. I just calculated the area of this part B, and the a of x is 4 minus that. So it's 4 minus b. It's 4 minus 4x plus x squared. Nobody helped me over chat. That's okay. So 4 minus b is actually 4 minus 4, which is 0, and then minus 4x, which is 4x, and then minus x squared. So when you take the derivative of this, you absolutely do get 4 minus 2x. So I was able to calculate this antiderivative just by using the area formula, which is super cool. I think that's really interesting. So I'll definitely ask you about that. And by the way, like, you can calculate this using fundamental theorem of calculus part 1. Nothing stops you from doing that. So let me show you how to do that too. This is integral from 0 to x of f of t dt. That's 4 minus 2t dt. So the way you would do this is just calculate an antiderivative of 4 minus 2t, which is 4t minus t squared, then evaluate it from 0 to x. See how much faster this is? Because when you do this, you plug in x, you get 4x minus x squared. And then you're subtracting, plugging in 0, which gives you 0. And of course you get the same answer. You have to get the same answer because they're equal. But this way of using fundamental theorem of calculus gave me the formula immediately, whereas using geometry took me a little bit more time. And in fact, I made a little mistake while I was doing it, so it took me a little bit more time to correct the mistake. So quickly using fundamental theorem of calculus, part 1, I was able to find that area formula. And general theory tells me I'm guaranteed that the derivative will be equal to 4 minus 2x, but I've also been able to verify just by calculating it. So that's the point of that question. That's really cool. Let me try to sneak in one more. Calculate the derivative. So this one's a classic. Sometimes you see it on placement exams for grad school. Let's take the integral from 1 to 1 over x, cosine cubed of t dt, and let's calculate the derivative with respect to x. So you see this problem on the exam, what are you going to do? So here's the issue. So if you were calculating the derivative of integral from 1 to x of cosine cubed t dt, then I hope that you would quickly say, because cosine cubed is continuous by fundamental theorem of calculus part 2, this derivative is nothing but cosine cubed of x. That's what that theorem says, that the derivative of this integral is the integrand. And this was my function, capital F of x. But here we've got something different. Like what you're really doing is taking the derivative of capital F of 1 over x, right? Because you've got 1 over x in the upper limit. And that does make a difference. So if I take maybe, say, g of x equals 1 over x, then that's like saying you're taking the derivative of f composed with g of x. And when you want to take a derivative of a composition of functions, you know that what you must do is use that chain rule. So that's f prime of g of x times g prime of x. F prime you figured out because that's right here. This is f prime of x. This is the derivative of f of x, right? So this is my definition of f of x, and there's its derivative by fundamental theorem of calculus. So you take the derivative and you plug in g of x. So I plug in g of x here, giving me cosine cubed of 1 over x, and then I multiply by the derivative of the inside function, the derivative of 1 over x, which is minus 1 over x squared. So rewriting that, that's minus cosine cubed of 1 over x divided by x squared. So that's the derivative of this function. So it's not quite so simple as simply like plugging in the upper limit into the variable. Since upper limit was itself another function, you had to use the chain rule. You had to take cosine cubed of 1 over x, but then multiply by the derivative of 1 over x. Okay, so that's a preview of at least 2 exercises that I found in the back of the book and found interesting. So what did we learn today? We reviewed Fundamental Theorem of Calculus Part 1. We stated and proved, or at least gave some good intuition for Fundamental Theorem of Calculus Part 2. We tried to make some arguments to connect them together and put it in perspective. And then we did 2 concrete examples, so 2 book problems, namely 5.5 number 1 and 5.5 number 34, to reinforce our learning. So that's it for today. I'll see you next time. That's going to be Wednesday at 11:10 a.m. So thank you, everybody. Have a great day.